Homework 6, problem 4, for a thick spherical shell with a locked-in polarization P that is K over R in the R hat direction. So it points in the radial direction, but it gets weaker as it goes out. Find the surface charge density and the volume charge density, sigma B and rho B, and using those, find the electric field E. And so this is a two-part problem. The next one will be finding the electric field using the electric displacement vector D. But first we'll go with finding the surface and volume charge and finding E. Starting out, we have that by definition the surface charge density is n hat dot P. And so on the inner surface, right, n hat is going to be minus r hat, and on the outer surface, n hat is going to be positive r hat. From that, we have two different expressions. We have sigma b inner is going to be minus k over a, and sigma b outer is positive k over b. There we go. For the volume charge density, rho b, we have the negative divergence of the polarization vector. In this case, we have to use radial coordinates to do this divergence. So the divergence in radial coordinates is 1 over r squared partial with respect to r of r squared times what our polarization vector is. So this is k over r, the r hat component of the polarization vector. So k over r. So this is the derivative simply of kr. That's just going to give k. And so this is minus k over r squared. And so rewriting that, we have that our bound surface charge is minus k over r squared. So we have that. Now, in order to find the electric field using these, we're going to use Gauss's law because we have a spherically symmetric charge distribution. So Gauss's law, of course, states that we draw a Gaussian surface that is a sphere, okay, spherical Gaussian surface. We're going to say that the radius of our Gaussian surface has radius little r, and then we're going to use the expression for Gauss's law, which is the flux through the surface d2x n hat dot epsilon naught e is equal to the charge enclosed, and for that it's the integral d 3x of rho, and that's it. That's what we're going to be looking at. So over some volume, and so that's what we're going to be looking at. Because we have a spherically symmetric case, of course, right, we say that E is equal to E in the r hat direction, and some r in the r hat direction. And plugging that in for us, we're going to have constant over this entire surface. N hat is, of course, in the r hat direction, so n hat dot E is going to be E sub r. It'll be constant over the surface, so that's 4 pi r squared times epsilon naught E sub r. This is going to be equal to the charge enclosed. That's what this volume integral of the charge density is. We know here that in the region 1 for A less than B, right, the charge enclosed is, or for R less than A, so this will be 0 for R less than A, but also, right, for R greater than B. Because this is a neutral dielectric, there might be bound charges on here, but we know they cancel out perfectly. So we have that. Okay, and then on the other end, we have to do a little bit more work. And so this is actually going to be equal to the total charge enclosed, which is going to be the integral d2x, right, of our inner bound surface charge, sigma inner sub b, plus then the integral d3x of our volume charge. And so simply evaluating those, this integral d2x of sigma b inner is going to be 4 pi a squared, and the minus k over a. So this is 4 pi minus 4 pi k a. There we go. This one, the integral, the 3x of rho b is going to be equal, this is only for, this one here is for a less than r less than b, right? So that's all our integral is going to be over, so I'm going to get 4 pi integral r squared dr, r prime squared dr prime, from a to little r. And then I have to plug in this, which is minus k over r prime squared. Okay, so the r prime squareds are going to cancel, and my integral is just going to be r minus a. And so this is, of course, going to be equal to minus 4 pi k r minus a. And so adding them together, this is going to be minus 4 pi k a. This is going to be minus 4 pi k r plus 4 pi k a. So those two are going to cancel. And what we're going to get for the electric field in this case, okay, so we have to go to the next page. What we're going to find is that the electric field everywhere, right, is going to be equal to the 0 for r less than a or r greater than b, and it is going to be equal to the 4 pi's are going to cancel, right? So minus k over r epsilon naught r hat, and that's it, and that's for a less than r less than b. Okay, so that is the electric field everywhere that we got by integrating the charge densities. For part B, find the displacement vector. Well, we have for our differential equation for the displacement vector that the divergence of the displacement vector is equal to the total free charge. In a spherically symmetric case, this of course turns into that same type of Gauss's law. So integral d2 x n hat dot d is total to the q free enclosed. But of course, there's no free charge at all in the system, so that's 0. By the statement, this thing has to be spherically symmetric, and so the only way that this is going to work out right is if d is always equal to 0 over the entire space. And so that's the first thing. We find that the displacement vector d is 0 over the entire space. Then we can use our expression for d. We know d, by definition, is E plus the polarization vector p. And so that says that E then is going to be 1 over epsilon naught b minus the polarization vector. Well, if d is 0, okay, that's 0, and this is minus the polarization vector over epsilon naught. Pulling that in, our polarization vector is k over r hat, and so we're going to get that the electric field is going to be equal to minus k over epsilon naught r hat, where we have the dielectric, and it's going to be equal to 0 because the polarization vector is actually equal to 0 where we don't have the dielectric, right? And so then E is equal to 0 minus 0 is still 0. And so this is for r less than a and r greater than b. And notice that's exactly what we had in the other case. And so, unsurprisingly, we get the same solution in both methods.